Hello and welcome to G Fun Facts Online, your home for the most fascinating stories science has to offer. Today, we're embarking on a journey that's 4.6 billion years in the making. We're going to be cosmic detectives, piecing together the origin story of our entire solar system. And our primary clues? They aren't found in ancient ruins or fossilized bones here on Earth. They're locked away in tiny grains of dust and rock, collected from millions of kilometers away, from the mysterious wanderers of our solar system, asteroids. This is the story of astrogeology, a field that is literally reaching out to touch other worlds, bringing back pieces of them, and using them to unlock the deepest secrets of how our planets, our water, and maybe even how we came to be. For centuries, we could only look at these celestial bodies through telescopes, faint points of light in the dark. But we are living in a golden age of exploration. We're no longer just looking. We are touching. We are collecting. This is the story of how bringing back pieces of asteroids is changing everything we thought we knew about our place in the universe. The field of astrogeology itself isn't brand new. Its roots trace back to the first astronomers mapping the moon. But it truly came into its own during the space age. A visionary geologist named Eugene Merle Shoemaker realized in the 1960s that the rules of geology on Earth could be applied to other worlds. He founded the Astrogeology research program, and his work on impact craters both here and on the moon laid the groundwork for understanding the violent, dynamic history of our solar system. The Apollo missions were the first game changer. For the first time, humans walked on another world and, crucially, brought back samples. Those lunar rocks were a treasure trove, confirming that sample return missions were the key to unlocking planetary secrets. But while the moon was our first taste, asteroids are the main course. Why? Because asteroids are the leftovers from the creation of our solar system. They are primordial remnants, time capsules, that have been floating, largely unchanged, for billions of years. By studying them, we can answer the biggest questions. How did planets like Earth even form? Asteroids are the literal building blocks. Where did Earth's vast oceans come from? Many asteroids are packed with water-bearing minerals. And the biggest question of all, what is the origin of life? Certain asteroids are rich in organic molecules, the very amino acids that form proteins. Could the ingredients for life have been delivered to a young Earth from space? For decades, our only access to this material came from meteorites, asteroid fragments that survived a fiery plunge through our atmosphere. While incredibly valuable, they're compromised. They get cooked on the way down and contaminated once they land. We often don't even know which specific asteroid they came from. This is why robotic sample return missions are so revolutionary. They allow us to go to a specific, well-studied asteroid and bring back a pure, pristine sample, a direct line to the solar system's baby pictures. And two recent missions have stood as giants in this new era: Japan's Hayabusa2 and NASA's OSIRIS-REx. Let's start with Hayabusa2. Launched in 2014 by JAXA, the Japanese space agency, it targeted a carbonaceous asteroid named Ryugu, about 900 meters across. Carbonaceous means it was thought to be rich in carbon and water, prime real estate for finding clues about the origins of life. Hayabusa2's visit to Ryugu was a stunning display of robotic precision. It didn't just orbit, it deployed little rovers and landers. And then came the heist. It performed not one, but two sample collections. For the second one, it did something incredible. It fired a copper projectile into the asteroid, creating a small, artificial crater. This allowed it to collect subsurface material, stuff that had been protected from the harsh radiation of space for eons. In December 2020, after a 6-year journey, a capsule from Hayabusa2 blazed through our atmosphere and landed safely in the Australian outback. Inside was just over 5 grams of Ryugu's surface. It doesn't sound like much, but it was a scientific treasure chest. Not to be outdone, NASA launched its own mission, OSIRIS-REx, in 2016. Its target was another carbonaceous asteroid, Bennu, a bit smaller at 500 meters in diameter. The goals were very similar. Understand the early solar system, find the source of water and organics, and get to know a potentially hazardous near-Earth asteroid a little better. When OSIRIS-REx arrived at Bennu in 2018, it got a surprise. The surface wasn't the smooth, sandy beach they had hoped for. It was an incredibly rugged, chaotic landscape covered in boulders. This made finding a safe spot to collect a sample a huge challenge. But in October 2020, they pulled it off. The spacecraft descended towards the surface and executed a maneuver called the touch and go, or TAG. Its robotic arm made contact for just a few seconds, releasing a puff of nitrogen gas to stir up the surface material, and a collector head gobbled it up. The maneuver worked almost too well, collecting so much material, an estimated 250 grams, that the collection head was jammed open, leaking a little bit of its precious cargo into space before they could secure it. Finally, in September 2023, 7 years after it launched, OSIRIS-REx flew by Earth and released its sample capsule, which landed right on target in the Utah desert. The arrival of these samples from 2 different asteroids marked the beginning of a whole new chapter. So what happens when this cosmic dust gets back to Earth? It's treated with more care than the crown jewels. In ultra-clean laboratories designed to prevent any contamination from Earth, scientists use a battery of incredibly sophisticated tools. They use electron microscopes to see the texture and structure of the samples down to the atomic level. They use various forms of spectroscopy, which is like shining a special light on the material to see what chemicals and minerals it's made of, identifying water and organic compounds. And they use one of the most powerful techniques, mass spectrometry, to measure the isotopic composition. This lets them determine the exact age of the material and trace its origins back to before our sun was even born. The results from analyzing Ryugu and Bennu have been nothing short of breathtaking. One of the biggest revelations is the overwhelming evidence that the parent bodies of these asteroids were once wet. Both samples are rich in clay minerals, which only form when rock and liquid water interact. The Bennu sample even contains salts, the telltale sign of evaporated brines. This paints an incredible picture. These weren't just inert rocks. Their parent bodies were geologically active worlds with pockets of liquid water warmed by radioactive elements. They were like little chemical reactors, a briny broth where complex molecules could form. And this leads to the most tantalizing discovery of all, the building blocks of life. In these pristine samples, untouched by Earth's atmosphere, scientists have found a whole zoo of organic molecules. They found numerous amino acids, including many of the 20 that life on Earth uses to build proteins. And in a stunning discovery, they found all 5 of the nucleobases that make up DNA and RNA, the molecules that carry the genetic code for all known life. This is powerful evidence for the idea that the raw materials for life weren't unique to Earth, but were delivered here from space by asteroids and comets billions of years ago. A fascinating little detail from Bennu is about something called chirality. Many molecules, including amino acids, come in 2 mirror image forms, like your left and right hands. On Earth, life exclusively uses the left-handed version of amino acids, and why that is remains a huge mystery. The Bennu samples contained roughly equal amounts of both left and right-handed forms. This suggests that life's preference for one-handedness happened here on Earth, after the ingredients were delivered. While the 2 asteroids are similar, there are also subtle differences in their color and the extent of water alteration, highlighting the diversity that existed in the early solar system. And the collaboration between the Japanese and American teams, including swapping samples, has been key to painting this more complete picture. The success of Hayabusa2 and OSIRIS-REx is just the beginning. The future of astrogeology is incredibly bright. China is entering the game in a big way with its TIANWEN-2 mission, set to launch in the mid-2020s to collect samples from another near-Earth asteroid, and then travel on to study a comet. The European Space Agency is focusing on planetary defense with its Hera mission, which will visit the asteroid that NASA's DART mission intentionally crashed into, to study how we might deflect a genuinely dangerous asteroid in the future. And looking further ahead, engineers are dreaming up even more ambitious concepts like Ambition, a mission to collect a cryogenic sample from a comet, keeping it frozen solid all the way back to Earth to study the most pristine, volatile materials from the dawn of the solar system. All of this will require incredible new technologies, faster propulsion, smarter autonomous spacecraft, and novel ways to drill into rock and ice in zero gravity. The study of these tiny grains of asteroid dust is more than just a science project. It's a journey into our own deep past. These samples are a direct link to the chaos and creation of the early solar system, a time when planets were being born and the seeds of life were being scattered among the stars. The secrets of the planets, locked away for billions of years, are finally being unraveled. And with every discovery, we get one step closer to understanding the grand cosmic story and our own place within it. Thanks for tuning in to G Fun Facts Online. Well, see you next time.